Okay, so in this PowerPoint, this video, we're going to talk about what to do when we have correlated data. So I have added this file to D2L. The name of it is Head Links from Two Researchers, and it is an Excel file. So what you can see is over here we have the first column, we have specimens. And what these are lizards. So there were basically 10 lizards. And then Harvey measured the length of the head. And then Shaney came along later and took the same specimens and measured the length of their heads. So notice this first specimen here, it's relatively small. And Harvey's measurement was a little bit smaller than Shaney's measurement. But then when you look at the second specimen, it's a larger specimen. Notice Shaney's measurement was a little bit smaller. So what we're interested in this comparison is we want to know, is there some sort of systematic error? In other words, does Shaney always or usually take measurements that are a little bit shorter or a little bit smaller than Harvey's, or are they maybe a little bit larger? So we want to know if there's a systematic error or if the differences between the two researchers is purely random. Okay, so at first glance, we've got these two sets of data here. So we have all these measurements that Harvey took, and then we've got all these measurements that Shaney took. So some people might say, well, couldn't we just do what we did in the previous video and just compare the means of these two things? The answer to that is no. That would almost certainly be a non-significant comparison. And the reason is that there's so much variation in here. I mean, look at this really big lizard here. So you've got like big specimens here and small specimens. So there's a lot of variation. The variance in here is going to be huge. And the two groups are almost certainly going to have a lot of overlap. So what we're interested in is if this measurement differs from this measurement, and if this measurement differs from this measurement. So the first step we might do is just compare the individual measures. Now we can do that easily in Excel. So what I'm going to do is I'm going to add a new column here where I take the difference between the two. So this column is going to be, Harvey's measurements minus Shaney's measurements. All right. So we're going to set this up to where we take, the data from Harvey. So that would be B2, and we're going to subtract the data from Shaney. So that one is C2. Okay. Now, to save time, you don't need to type that in all the way down. You just select this. You hit Control-C to copy. Then you drag down and hit Control-V to paste. Okay, so now we can see some of these values are positive and some of these values are negative. All right. Now, what is the null hypothesis we're actually testing here? So what we want to know is, are these random or is there a systematic difference? So if there's really no effect, they should be random. And if they're random, when we average these, it should be close to zero, or at least the sampling distribution would be zero. And then just by chance, sometimes the average will be a little positive and sometimes the average will be a little negative. Now imagine if Shaney always took higher scores. Then this would be a very large negative number because they would all be, the same. On the other hand, if Harvey always took larger scores, it would be a large positive number. Okay, so the first step then is to average these, all right? So we're going to basically find a mean of the differences. All right, so let's see, average. All right, so what we need is we need D2 to D11. All right, see how it's highlighted? That will give us an average score. Okay, so you can see that doesn't deviate very much from 0. That makes me think this is almost certainly going to be a non-significant comparison, because what we're assuming is the average is going to be, see, look at the null hypothesis, the average is going to be 0. So we're comparing this to that. All right, so in order to do this, now we're working with samples, so we don't know what the standard deviation is. We need to estimate the standard deviation. So I'm going to put that here. I'm just going to abbreviate it as SD. All right. And you just do STDEV. Then we need D2 to D11. Okay. All right. Enter. Okay, so we're going to use a t-statistic to determine, if this value is significant. So in other words, we want to know if this is a significant deviation from our hypothesized value. So we're going to need a standard error to do that. So I'm going to put here standard error. Remember that the standard error is equal to the standard deviation divided by the square root of n. So you can calculate that directly here. Let's see. So we want D13, all right, over, and then you have to put a little thing like this, square, no, actually, let's see. I think it's SQRT, like square root, and then you put n, so there's 10 of these specimens. All right, put that in there. Okay, so that gives us the standard error. All right, now remember how we calculated t-statistics in the earlier PowerPoint? We're going to use the same formula here. So the t-statistic is going to be the sample statistic minus the hypothesized value, right, divided by the standard error. So again, Excel can calculate that for us pretty easy. So it is equal to, let's see, D12, right? That is our statistic we actually calculated. Oh, hold on, you got to put this in parentheses. Let's see. D12, all right, minus the hypothesized value, which is just 0, so we could have just put in D12, but I'm going to do that for completeness. Okay, divided by the standard error, which we have here in D14. All right. Okay, so that'll give us a t-statistic. Okay, now notice this t-statistic is negative. What does that negative sign mean? All that means is we set this up by subtracting Shaney's score from Harvey's score. We're really just trying to figure out if there's a difference between these two researchers, so we could have done it the other way around. We could have subtracted Harvey's score from Shaney's score, and we would get positive numbers. So when you're working with these t-statistics, frequently, depending on how you set it up, you'll get a negative score. That doesn't mean anything. So ignore the sign of the t-statistic. And when you report a t-statistic, don't put a negative sign because it is meaningless. Okay. All right, so what do we want to do now? Let's see. So we're going to look up the probability. All right. So to avoid a rounding error, we can copy this. Let's see here. Yeah, we'll just go ahead and add this directly. Let me see. Trying to think how we can do this without getting a rounding error. So remember, ideally, we don't want that. We just wanted to use the decimals here. Let me see what happens here. I'm just going to try this. This is probably going to introduce a little rounding error somewhere. Let's see what happens here. So we'll go to Lane's calculator. You're going to just, pop that in. Let's get rid of this stuff we don't need here, again, to avoid a rounding error. Remember, all you need is just the dot. Now let's see what what we've lost here. 0.68 or 0.69, that'll probably be enough. Let's add that in there. 0.69. Oh, whoops, that won't get it. So let's just put there. Okay. Now I've gotten as many decimals in there or as many digits in there as I can to avoid a rounding error. Let's see. Degrees of freedom. Okay, let's go back to this. Now, for degrees of freedom, notice that we've only calculated or estimated one standard deviation. So we only lose 1 degree of freedom. Also, even though there may be 20 data points over here, we're only looking at those. So this is 10 data points or 10 scores. We lose 1 degree of freedom. So that gives us 9 because we only calculated 1 standard deviation. So that means that the degrees of freedom, I'll just put it here, is in this case equal to n, which is 10, the 10 data points, minus 1 because we only calculated 1 standard deviation. All right, and that's equal to 9. Okay. All right, now let's see. So we'll go back to Lane's calculator here to get the probability. So we put in 9 here and calculate. So there's the probability, the two-tailed probability. It's obviously very high, which means we can't reject the null hypothesis. All right. So what should we say then? All right, well, we're going to report this, so I'm just going to copy it now, so I'll have it in a minute. So our results here. Conclusion. Okay, what would you say? Well, should we say the differences are random? Is that what you should say? Definitely not. Notice if you say this, hold on just a second here, if you say that, then you are accepting the null, or you are saying that you've proved the null hypothesis. Remember, we can never do that. There may be a systematic error between these two researchers. The problem is we've only got 10 data points. So if we had a larger sample size, like if they would have measured 1,000 lizards and it was still a negative score, then maybe we would have enough to reject the null hypothesis. No, once again, all you can really say here is we fail to reject the null hypothesis, or in this case, we did not find a systematic difference in the measurements. Something like that, right? And then I'm just going to go to the next row to finish this. As always, we would want to put our statistics. So here we would have T and subscript 9, or I'm sorry, subscript 10, right, for the sample size, equals to, remember, don't put a negative score there. So 0.712, all right. And then the probability that we got, so that's, I looked that up, so I'm just going to paste it in here and go back and fix this so it doesn't look too sloppy here. Probability equals, we're going to round off to 3 decimal points, so that would be 495. Okay. So from the way we've written this answer here, a reader can see that, the sample size was 10. Remember, make that a subscript. I didn't bother to do that because it's hard to do in Excel. And, we've tried to round off the other things here. The rounding off would reflect the precision of the measurements. But I always do 3 decimals on tests, so I'm showing you guys how you would write it on a test. Okay. So that concludes this little section on correlated t-test. Now I want to talk about what you do when you have multiple comparisons. So we're going to go back to the whiteboard to see how to handle this. So I'm just going to rearrange the camera for a minute, if you'll bear with me. Okay, so we'll start up here, and then we'll move down the board. I've already worked out this particular problem. Okay, so this is like an independent groups test, but what do you do if you have more than 2 groups? So for situations like that, we almost always use something called the Tukey statistic. As we're going to see, there's a way to do this with t-statistics, but you have to adjust the probability. Okay, so first we'll talk about the Tukey test. All right, so if you have more than 2 groups, so let's say instead of just testing 1 fertilizer, we're testing 2 fertilizers, all right, or maybe 3 or 4, more than 2. So then the null hypothesis becomes something like this. The mean of the first fertilized group is equal to the mean of the second fertilized group, etc. If you look at any single pair, the difference between those is 0. And how you compare these things depends really on what you're interested in. Are we interested in comparing each one of these to the unfertilized group? Do we want to compare the individual ones? So we can make multiple comparisons. All right, and that's when we use t-test. So, for example, let's say we have we'll look at like 3 of them, for example. What if we wanted to compare our first group to our second group, but we also wanted to compare our first group to our third group? The problem with this is that it inflates the type 1 error rate, or it inflates alpha. So if we just did a normal t-statistic, like we generated a t-statistic using this comparison, and then we also generated a t-statistic using this comparison, you can't use those probabilities that you would find because alpha has been increased. So you can't just use those probabilities directly. I'll show you what you can do with those probabilities in a minute. But the problem is that alpha becomes inflated, so you can no longer just compare those probabilities to 0.05 and see if they're significant. This is the difficulty there. All right, so let's see what we would do instead. All right, we calculate a different statistic called Tukey's statistic. So here is the formula for it. It's pretty similar to the formula we use for a t-statistic. So let's look at what's different here. So just like in a t-statistic, we take our statistic, we calculate it like a mean, or a difference between means actually, minus a hypothesized value, which is 0 right? And then we divide by something that looks like the standard error. Remember that the standard error for a t-statistic was 2 times the mean squared error over n. Here is just the mean squared error over n. What's missing is the 2. And this is what we call little n. This is like the number of data points in each group. So you may remember we had 20 plans in each group last time. So that's what would go there, 20, if we were doing that for using the same sample sizes. And then the degrees of freedom is also very similar to the way we would calculate our groups using a t-statistic. So remember, it's like all the plants, right? Minus the number of groups. So when we were doing the independent groups test, we had 2 groups. So what we had like 40 plants minus 2 groups gave us 38. This time around, if we're working with 3 groups, we'd have 60 plants minus 3 groups, so it would be, for the 3 groups, 20 in each group would be 60 minus 3, you see. So that would be 57 if you're making 3 comparisons. All right. So let's actually look at an example then of how you would calculate this thing. All right, and that's what we have here. So I have a different example in the PowerPoint, but it's pretty similar. Sort of the first step is you want to kind of accumulate all your data. So I've just taken 3 groups here. Remember, this can be done for more than 3. You can do as many as you like, really, I guess. All right, so what we need to calculate the Tukey statistic is we need to tabulate our means. We need to get the variances, all right? So not the standard deviations, the variances, because it's easier to put it in here. And then we need to know what the sample sizes are. So you have to be able to do this by hand when the sample sizes are equal. All right. Now it is possible to calculate Tukey statistics when sample sizes are unequal, but we use PASS for that. So doing that by hand is much too complicated. The same is also true for independent groups t-test. There as well, you can use unequal group sizes, but we use PASS to make those calculations because they're really a pain to do by hand. All right, so here we have the calculation of the Tukey's Q statistic. All right, so we're going to compare these 2 groups first. So we're going to compare fertilized and the first fertilizer and the second fertilizer. So we take the difference between those. Notice that's 2. But hypothetically, if neither of them is having any effect, it should be 0. That's our hypothesized value. All right. Now we put that thing in there, right? Square root of the mean squares error over n. So remember, what's missing here is the 2. All right. So we take the difference between the means here. Remember, that's 2. All right. And then here is the square root. So we're going to average all 3 variances. Even though we're comparing just these 2 groups, we average the variances for all 3 of the groups. In other words, I'm assuming that we're making all possible comparisons. So what that means is we're comparing group 1 to group 2, but later on we're going to compare group 1 to the unfertilized group. We're going to compare group 2 to the unfertilized group. So that's 3 different comparisons. We're making all those comparisons. I'm just going to show the calculation for one of them because you can do the other ones on your own, I suppose. At any rate, so we put all that in here. All right, so here are the 3 variances. There are 3 of them. And essentially what we're doing is we're averaging the variances. And then we're dividing by n the sample size of 20. Okay, that's in each group. That's little n. All right. Now when you calculate all that, I got 2 even. So you can double check my math if you want. But but that's what I got when I did this. All right, so now we're going to see what we do next. So next, we're going to actually go to Lane's calculator here for the Tukey statistic. So let me just pull this up, and we'll put it over here. You guys will give me a minute here. I will open this. So we'll close the other example we were doing here. All right. So this is a different calculator. This is number 11 down here. It's called the studentized range distribution. Let me be sure you guys can see this thing okay. I think that looks all right. So you click on the studentized range, and notice that the calculator is kind of similar to what we saw for the t distribution. All right. So what we need is Q. Now this you would paste in normally, but since I got a 2 evenly, I'm just going to enter that. So that's what I calculated for Q. All right. Now we need the number of means. So for this example, we were working with 3 groups. So there's 3 of them. All right. So it's not the number of means you're comparing, it's how many groups you have. I don't know why they didn't just call that groups. That number of means is a little confusing to me. Okay, all right, so degrees of freedom. Now remember, we take all of the plants in all 3 groups. Remember there's like 60 plants total. And we subtract the number of groups. There are 3 groups total, so this should be 57. All right, enter 57. Hit calculate. Okay, there's the probability. So we compare that to, 0.05. Since it's less than 0.05, we are going to reject we are going to fail to reject the null hypothesis. So this is a non-significant result. Okay, let me go over here and show you how you report it. All right, let me see if we're in focus here. Okay, looks good. All right, so there was the calculation of the degrees of freedom. So we had big N this time, all the plants we had minus the 3 groups, all right, 57. This is how you report it. So we did not find a difference between the 2 fertilizers. This is just a comparison between the 2 fertilizers. Now, what do you put here? So definitely we need the Tukey statistic, all right? Some people like to put the 2 samples, like the 2 sample sizes, so 20, 20. On the other hand, some people prefer to put like the number of groups and the degrees of freedom used in calculating this statistic. When we get to this, I don't really have a preference of which one of these you use. If you were going to publish a scientific paper, you always, in the methods, you always have to tell people what subscripts mean, because otherwise they have no idea what you're putting there, so at any rate, so you can use either one of these. I don't really care. For this, when we're working with these Tukey statistics, I'm just going to look to be sure you have the right statistic. All right, and then you have your probability, always got to have that, okay? Anyway, that's how you generate a Tukey statistic. Okay, now, what if instead of using a Tukey statistic, we had used a t statistic? What can you do, or can you do it at all? The answer is yes, you can, but you have to make something called a Bonferroni correction. Okay, so we're going to go through that using these same individuals. All right. So this time, and this will be nice because it will allow us to compare these 2 things. This time, we're going to generate a t statistic and make a Bonferroni correction. All right. So for a t statistic comparing, groups 1 and 2, we're going to have the same thing here. 1 over n, etc. Okay. Now this time we have 2 times